Lesson number 21, daily summary. In this lesson, we solve quadratic equations by using the square root property and by factoring. How can we solve this equation that's already in factored form with 0 on one side? 3x minus 1 times 2x plus 7 equals 0. Okay, if you pick your favorite number for x and you plug it in here, 3x minus 1 is just a number. And so I'm going to cross this off. Actually, I'm going to cross this off here and just say, in my mind, that is some number. And I'm going to cross off the other one. Again, you pick your favorite x, you put it right there. And 2x plus 7 is just some number. So at its heart of hearts, this is the product of two numbers, right? For any given x, you're just multiplying two numbers together. And in this case, the product of those two numbers happens to be 0. And we can say something very concrete if you know that you have two numbers that multiply together and give you 0. What you can say is that at least one of those two numbers must have been 0, right? Maybe it was 0 times 31, that gives you 0. Maybe it was negative 17 times 0, that gives you 0. But the only way you're going to get 0 from multiplying two numbers is if one of those numbers is 0. And so that means we can trade this kind of complicated single equation for two simpler equations. Either 3x minus 1 is 0, which we write as its own equation, or 2x plus 7 equals 0. And then we solve those two simpler equations, which we could have given you on the very first day of this semester, and you would have solved with no problem, right? In this first equation, you add 1 to both sides and then divide by 3. So you get x equals a third. In the second equation, subtract 7 from both sides and then divide by 2, and you get x equals negative 7 over 2. And those are your two answers to this original equation. The 0 there is not chosen coincidentally. The 0 is the only number that we could have done this kind of thing with. Suppose that I tell you I have two numbers that I multiply together and I get 18. Can you guarantee that one of my two numbers is 18? No. What could the two numbers have been? Well, it could have been 3 times 6, right? Neither of those numbers is 18. Could have been 2 times 9. Could have been 18 times 1. Could it have been anything else? Yeah, sure. It could have been like negative 3 times negative 6. That gives you 18. What if I wanted one of the numbers to be 7? Could you still get 18 by multiplying by something? Yeah, if you give me a fraction, 18/7. That has the right product. So two numbers multiplying to 18, that doesn't tell me anything. The two numbers could be anything, right? Like there's no guarantee that one of them is 18. Could be that one of them is 18, but you don't know anything. Nothing concrete. But in the case of 0, 0 is this unique special number that if you multiply two numbers and get 0, for sure one of the two numbers must have been 0. Okay, number 2, a quadratic equation written in the form ax squared plus bx plus c equals 0 is said to be in standard form. A, b, and c are just constants. X is really the variable. And it turns out standard form is pretty useful, so getting one side of a quadratic equation equal to 0 is often a good first step. So let's take a look at this example. X squared minus 24 equals 5x. I want 0 on one side, so we're going to subtract 5x from both sides. I'm going to intentionally write these three terms in a particular order. I like my x squared first. I like my x term second. So when I subtract that 5x, I'm not going to put it after the 24. I'm going to put it in the middle here. And then I've copied the negative 24 right there. And now it's equal to 0. Don't leave that 0 off. You start with an equation. Whoops. Started with an equation right here. Every single one of the lines after it is going to be equation, not expression, equation. Okay, so that's our standard form. We'll do this later on when we get to the quadratic formula, but just to connect to this kind of wacky ax squared plus bx plus c equals 0, a is the number touching x squared, it's 1. B is the number touching x, that's negative 5, and c is the number that's not touching any x's, that's negative 24. So that's what we mean by a, b, and c. They're just the specific numbers touching x squared, x, and the constant in that order. Okay, so what do you do once you've got it written in this standard form? Well, you factor. And in this case, again, we go through the factoring in the same exact order every time. Greatest common factor of those three terms on the left-hand side is 1, so there's nothing to do there. Is it a difference of 2 squares? Nope, it's 3 terms. Nothing to do there. So then the only other option is the 2 by 2 box. I'm not going to give the details here. You can do it later on. But if you use the 2 by 2 box, you will get x minus 8 times x plus 3. And now it's in our really nice form. It's factored. And multiplying two numbers to get 0, you can guarantee that one of those numbers must be 0. And so we write those two separate equations, x minus 8 equals 0, or x plus 3 equals 0, and then we solve for x. Add 8 to both sides in the first one, so we get x equals 8. Subtract 3 from both sides, x equals -3, and we're done. Number 4, using a box isn't our only factoring technique, so look for opportunities to factor with the GCF or dots before trying the box. For example, 10x squared equals 35x. All right, so this one's typed out over there, but let's just do it. 10x squared equals 35x. Okay, typically I like 0 on one side, so let's move the 35x from the right to the left by subtracting. 10x squared minus 35x equals 0. Don't forget the equals 0. First kind of factoring we do is not the 2 by 2 box. It is the greatest common factor. For 10 and 35, that's a 5. X squared and x, they both have x. You can't take out any more. They don't both have x squared, but 5x is the greatest common factor. And when I pull that 5x out of the 10x squared, I got 2x left over, and minus just a plain 7. Still equal to 0. We don't need parentheses around the 5x, but I'm going to write it so that this one looks just like the one we previously did. And now I have 2 parentheses multiplied together, giving me 0. So one of those things must be 0. So let's write our 2 brand new equations. Either 5x is 0 or 2x minus 7 is 0. In this first equation, we divide both sides by 5. And 0 divided by 5 is still 0. In the second equation, it's 2 steps. Let's show our work here. Add 7 to both sides. I get 2x equals 7. And then finally divide both sides by 2. And we get x equals 7 over 2. Those are our 2 answers. X is 0 or x equals 7 over 2. Some of you have seen problems like this in a past math class, and you have developed a shortcut. And your shortcut, we can look at this x minus 8, x plus 3, 1. If I just look at this -8 and treat it like a number, what did the answer turn out to be? Well, it turned out to be +8. So -8 in the parentheses became +8 as an answer. +3 in the parentheses became -3 as the answer. So what's our shortcut here? Well, I guess you could just say whatever number is in the parentheses right there, you just take the opposite of that number and plop it down as your answer. Easy peasy. Problem is that shortcut is not always valid. Let's take a look at the one we just did. Take a look at this number right here. The number in the parentheses is -7. If we were to apply that shortcut, our answer would be +7, which is not the answer to this problem. The answer here is 7 over 2. Forget the shortcut. It does not always work, so really what good is it? It doesn't take long to solve these equations. Just write out your steps like we did there in orange. Get the right answer. Okay, on the next page, certain quadratic equations can be solved with a technique that's simpler than the factoring method. In order to solve the equation x squared equals 16, we need a way to get rid of the square on the x. The opposite of squaring a number is taking the square root of that number. So we'll take the square root of both sides of the equation. So starting with x squared equals 16, take the square root of both sides of the equation. Square root of x squared, that's just x. Square root of 16 is plain old 4, so x equals 4 is our answer. And that makes sense, right? If you do 4 squared, you get 16. That's great. Are there any other answers? Are there any other values of x that you can take that x value and square it and get +16? And I'm hoping you realize, yeah, there is another answer. It's -4. If you were to take -4 and square it, that means -4 times -4. 2 negatives make a positive, 16 in this case. So by doing this square root of both sides, we got only one of our 2 answers. We got just x equals 4, and we lost x equals -4. So it's written here in bold and italics. That's the best I can do to call attention to this important fact that is very often overlooked by students. When you take the square root of both sides of an equation, you must put in a plus or minus. I'll say it again. When you take the square root of both sides of an equation, you must put in a plus or minus. Now I caution you against like putting plus or minuses in everywhere where they don't belong. If I ask you for the square root of 81, that's just 9. It's not plus or minus 9. When we write that square root symbol, we are indicating the positive square root of the number. In the our previous class, we did stuff like, like 4 plus square root of 48 divided by 8, something like that. Oops, too many 8s. Don't put in a plus or minus there. Like, we're not actively taking a square root of both sides. You're just taking a given expression and you're rewriting it. There's no call for putting plus or minuses every time you see a radical. But if you bring a radical into the process, if you bring a square root in, that's when you got to bring in the plus or minus. It's really, really easy to forget, despite the fact that I put it in bold and italics. So here's something else I will share that will hopefully help you remember. I'm going to tell you something called the fundamental theorem of algebra. Now, this theorem is not technically part of our course, so if you tell somebody else that I shared this with you, I will deny it. The fundamental theorem of algebra is named appropriately because it gives you a sense of how important we think this thing is. There's exactly one theorem in all of math called the fundamental theorem of algebra, and here's what it says. It says if you're solving an equation, like this, x squared equals 16, or the ones we solved on the previous page. They're called polynomials, but the word doesn't matter. But if you solve an equation like that, then whatever the highest power is, that's how many answers the equation has. That's how many solutions the equation has. So as soon as I see an equation with an x squared there, if that 2 is the highest power, there are 2 solutions. Not just x equals 4, but x equals 4 and negative 4. 2 solutions. Coming back to this equation right here, I didn't need to do any work on this equation. As soon as I see the highest power of 2, I expect 2 answers all day, every day. Highest power is 2, 2 answers all day, every day. For much of this semester, we have solved linear equations. 8x minus 3 equals 5x plus 7. What's the highest power of x you see anywhere? It's 1. It's invisible. How many answers have we been getting to all of the equations we've solved this semester? 1, up until today, because every equation we solved was linear. First power, 1 solution. I won't give you any equations this complicated, but if I gave you like 2x cubed plus 7x squared minus 4x plus x to the 5th equals 9. How many solutions would we get if we could solve such a beast? Okay, looks like 3, that's the first thing, but that's not the highest thing, so don't get distracted. The order doesn't matter, it's just whichever is the highest power. It's 5 in this case. This equation right here has 5 solutions. Finding those 5 solutions is a whole heck of a lot of work. There is a formula and a process that can help you do it. But anyway, the highest power right there is for sure the number of solutions. I'm hesitating here because the x to the 5th thing, I just promised you there was a formula and a process, and I'm realizing I'm off by 1. There is a formula and a process for solving something with a 4th power up there, and there's also one for solving something with a 3rd power. The quadratic formula we'll see soon enough, but you might have seen before, will help you solve any quadratic equation. But it turns out there's actually no uniform process to solve every equation of degree 5. That degree is the highest power. I'm not saying you can't solve any equation with the highest power of 5. I'm just saying there's no process that will solve every single one of them, like a quadratic formula will solve every single quadratic equation. And there's no process for solving equations where the highest power is 6 or 7 or anything higher than 5, actually. 5 or higher, I should say. Okay, so that was a little detour to the fundamental theorem of algebra. Don't tell anybody I shared that with you. Okay, so what do we do here? Let's take a look at number 8. We're going to solve, actually 9. Let's solve this equation right here. So we are going to eventually take the square root of both sides of this equation, just like the x squared equals 16 equation. And the reason that I know that's a valid technique here is because this equation is missing the x term. Take a look up here. X squared equals 25x. That has an x squared, groovy, but it also has an x term. As soon as I see an equation with an x term in it, I can't do this square rooting technique. But if I happen to get lucky and see an equation with no x term in it, x squareds but no x, then I can do this square rooting technique like here. I've got x squareds in a couple of places, but no x terms. So first thing we will do is get the x squared terms together on one side. Let's move them to the left-hand side. We'll subtract 3x squared from both sides. So that gives me 4x squared minus 1 on the left. That's right here. And then just the 199 remains on the right-hand side. Still trying to get the x squared isolated. So let's move that 1 to the other side by adding 1 to both sides. So 4x squared equals 200. Still trying to get the x squared by itself. So let's move the 4 to the other side now by dividing both sides by 4. And finally, we get x squared equals 50. Fantastic. Now that it's x squared equals 50, I can apply the same technique that I did for the x squared equals 16. We will take the square root of both sides of this equation. When we take that square root, we'll put the square root there, we'll put the square root there, but then bold and italics, it says put in the plus or minus at that moment, this plus or minus right here. So we get x equals plus or minus the square root of 50. That is a perfectly good answer. 50 is not a perfect square, but we are obligated to simplify the square root of 50 as best we can, and the way that we do that is to find the greatest perfect square factor that goes into 50. So what do we have here? 50 is really 25 times 2. It's 5 times 10, but 5 and 10 are not perfect squares. 25 is. So then just copying this plus or minus here. This is our product property for radicals. And then square root of 25 is just plain 5, no more radical. And then the 2 stays inside. So plus or minus 5 square root of 2 is our answer. For sure, we expected 2 answers from the very beginning of this problem because the highest power anywhere was 2.